All right, hey everybody. In this section, we're going to think a little bit back to one variable calculus and linear approximations. And this is, of course, related to the equation of a tangent line for a function of one variable. Now we're looking at functions of several variables, and the higher dimensional analog of a tangent line would be a tangent plane. And so we're going to kind of generalize this idea of a linear approximation from single variable calculus to multivariable calculus. So just to recall, a plane passing through some point x0, y0, z0 is going to have the equation of the form a times x minus x0 plus b times y minus y0 plus c times z minus z0. Now, we used lowercase a, b's, and c's in the past. I'm going to leave these capital here because I'm going to show if you were to divide everything by capital C, you'd have a over c blah, blah, plus b over c. We're going to let capital A over c, call that lowercase a. So we can rewrite this as z equals, or z minus z0 equals a times x minus x0 plus b times y minus y0. Actually, what I should have said is if we were to divide that previous equation by negative capital C, then little a would be capital A over negative C, and so forth. But anyway, just to show you, you can rewrite the equation like this. In fact, you could even write z equals z sub 0 plus a times x minus x sub 0 plus b times y minus y sub 0. So now let's consider that z is some function of x and y. Okay, so we're looking at z as a like you could think of these points x, y, z on this surface. Well, the tangent plane at the point x sub 0, y sub 0, and then f of x sub 0, y sub 0. Now if we fix y equals y sub 0, then we're going to get the equation of this tangent plane, z minus z sub 0 equals a times x minus x sub 0. Realize that that a is actually f, the partial derivative of x, a partial derivative with respect to x at x0, y sub 0. And if we fix x equals x sub 0, then you get z minus z sub 0 equals b times y minus y sub 0. So b is fy, the partial derivative with respect to y at x sub 0, y sub 0. So what we can write for the tangent plane so we can write the equation for a tangent plane at this point, z minus z sub 0 equals partial derivative with respect to x, x sub 0, y sub 0, right, at that point, times x minus x sub 0 plus the partial derivative with respect to y times y minus y sub 0. So let's do an example. So let's, as an example, take a look at the paraboloid z equals 2x squared plus y squared, and we'll find the equation of the tangent plane at the point 1, 1, 3. So the partial derivative with respect to x is going to be 4x, and the partial derivative with respect to y is going to be 2y. So the partial derivative at the point 1, 1 with respect to x is going to be 4, and the partial derivative with respect to y at 1, 1 is going to be 2. So the equation of the tangent plane, just following from the previous formula, z minus 3, that's z sub 0 is 3. Z minus 3 equals the partial derivative with respect to x, it's a 4 times x minus 1 plus 2 times y minus 1. So that's the equation of the tangent plane at 1, 1, 3. Okay, so pretty straightforward. So just as we used a linear approximation with function of one variable, you could use a tangent plane to approximate z near some point AB. And so the linearization is f of AB plus the partial derivative with respect to x times x minus a plus the partial derivative with respect to y times y minus b. So this is what you call the linearization of the function f of x, y equals z, right, at AB. Okay, so if the two partial derivatives exist near a point AB, and as long as those two partial derivatives are continuous functions at AB, then we would say that the function f is differentiable at AB. Or I should say, then the function is differentiable, following the definition of differentiable. This theorem says that all you need is the two partial derivatives to exist and be continuous. So let's take this example, f of xy equals x e to the xy. So I want to show that the partial derivatives are first of all that they exist at I'm going to use the point 1 comma 0. So f x, the partial derivative with respect to x, is going to be I have to take the derivative of the first part times e to the xy, so that's going to be 1 e to the xy plus x e to the xy times the derivative of xy with respect to x, which actually is going to give me a y. And the partial derivative with respect to y is going to simply be, let's see, x e to the xy, the derivative of that exponent, because we're treating x's as constants now, right, would be another x. So actually it's going to be x squared. Both of these exist, and they're both continuous functions because they're just exponential functions, right? Defined everywhere. The domain is everywhere. The domain is all of R2. So therefore, this original function is differentiable. And so we can find its linearization. The linearization of xy for this function, it's going to be f of 1, 0 plus fx at 1, 0 times x minus 1 plus fy of 1, 0 times y minus 0. That's the equation for linearization, which I'm gonna put everything in. If we plug in 1 and 0, we're going to get 1 times e to the 0 power, which is just 1, plus when you plug in 1, 0 for the partial derivative with respect to x, we're going to, once again, you're going to get 1 times x minus 1 plus the partial derivative with respect to y. Plug in 1 and 0, you're also going to get 1 y. So this is just 1 plus x minus 1 plus y, which is x plus y. That's the linearization of this function near the point 1, 0. And so to kind of further the example, if we wanted to approximate f of 1.1 comma negative 0.1, this is going to be approximately, right? Approximately the linearization of 1.1 negative 0.1, which is just 1.1 plus negative 0.1, it's 1. So this function, if you were to evaluate it at this point, it should be pretty close to the value 1. So I want you to think back to the idea of differentials. I'm going to try to illustrate it with this little diagram. If you recall, if you're interested in the, let's say this is this difference here, dx equals delta x. You might recall this, that the change in the value of the tangent line is going to be what you call dy, whereas the change in the value of the function is what you call delta y. So the dy, so dx and dy are the differentials, right? Now, we are going to kind of take this idea and think of it in terms of the tangent plane. Okay, so we're going to talk about this. Think about the relationship to this in the kind of the higher dimensional sense. So if this here is the point 1, 1, 0. So we're looking at this function that we actually looked at a little bit ago, which was 2x squared plus y squared. Okay, this paraboloid. Now this is maybe this, if we go out in this is the difference of a dx, and this is the difference of a dy. Okay, which take us to this other point, which would be 1 plus dx, 1 plus dy, 0. Okay, if we were to go straight up, this is the function, so that takes us to the point where on the point, the tangent point, right? Well, I'm going to go up to when I go up to so this here point is on the tangent plane, and so this would be the point 1 plus dx, 1 plus dy, and then the linearization of 1 plus dx, 1 plus dy. Whereas this point over here is actually the point 1 plus dx, 1 plus dy, and then f of 1 plus dx, 1 plus dy. Okay, like the actual point on the paraboloid. Okay, so just to kind of, I want to illustrate, if I was to go out, take this distance, I'm going to try to move out to approximately here, which is at this point here. That's like the same distance up as this point here. I've kind of moved there. Now I'm looking at when we've moved x and y from the point 1, 1 to the point 1 plus dx and 1 plus dy. You can see there's been two changes. First, there's been this smaller change. This is what you call dz. This is the differential, the total differential dz, and then this which is the change in the actual function of, that's the delta z. All right, so these are the visually what dz and delta z would be. Now let's look at the numbers. So for z equals f of x, y, the differentials dx and dy, we're going to let them be independent. The total differential dz is partial derivative with respect to x at xy dx plus partial y dy. So it'll be, or partial z over d over x dx plus partial z over dy, or partial y dy. That's the total differential, which in the end, it's actually, you could think of this as this is like the change in the height of in the z value of the tangent plane when you're going from AB to this new value xy. So this could be written as fx AB times x minus a plus fyab times y minus b. Whereas the delta z, right, this is, it's simply going to be the f of x plus, I guess we'd say delta x, comma, y plus delta y minus f of x y, which is to say that's the, so delta z would be the actual change in the function f when you move from this one point to another point by a matter of delta x, delta y. Whereas the differential would be the change in the height of the tangent plane, right? Okay, so let's let z equal x squared plus 3xy plus y minus y squared. So I want to find dz. Now, following what I've just looked at, the dz is going to be the partial of this function with respect to x. So that's going to be 2x plus 3y times dx plus the partial with respect to y, which is going to be 3x minus 2y dy. So that's dz. And so if I wanted to, so if xy changes, so if xy changes from the point 2.3 to the point 2.05, 2.96, I'm going to find dz and delta z. Dz is going to be, so in this case, the x, the y is going to be the starting point, which is going to be, so I'm going to have, like, the x is going to be 2 and the y is equal to 3. The dx is going to be the change in x, which is the 0.05, and the dy is the 2.96. I'm sorry. It's negative 0.04. So plugging that stuff in, it's going to be 2 times 2 plus 3 times 3 times 0.05 plus 3 times 2 minus 2 times 3 times negative 0.04. So the nice thing is that this is all gone, and so what we get is 2 times 2 is 4 plus 9, that's 13 times 0.05. Delta x, or sorry, delta z would simply be z of 2.05, 2.96 minus z of 2.3. So we just kind of evaluate that. Comes out to be 0.6449, which is close to 0.65. And so you can use these differentials to give you approximate maximum errors when you're using linear approximations, just as we could when we had functions of one variable. Take another example. Here we have a right circular cone, which is to say it's a cone with a where the going straight up, it meets the base at a right angle, right in the center. It's measured to have a radius of 10 centimeters, so I'll put that here at 10, and a height of 25 centimeters, but there's a possible error of 0.1 centimeter in each of these two dimensions. We want to estimate the maximum possible error in the calculated volume using differentials. So the volume is, remember, it's 1/3 pi r squared times the height. That's the volume of a cone. So we're going to take the derivative of everything, or in terms of differentials, right? So we're going to have dv equals 1/3. So what I'm going to do is I'm going to calculate the partial with respect. Now this, okay, let's take a step back. This is my function of R and H. Okay, so I'm going to find the total differential, which is going to be the differential, the partial derivative with respect to R times dr plus the partial derivative with respect to H dH. Okay, so writing this out, dv, the total differential, is going to be the derivative with respect to R. Well, that's going to 2 is going to come down. So it's going to be 2/3 pi times RH dr plus the partial with respect to H, which is going to be just 1/3 pi R squared dH. And now we're going to plug in the values where dr equals dH equals 0.1. So those are the differentials in the 2 dimensions. So we're going to have 2/3 pi times 10 times 25 times 0.1 plus 1/3 pi times the radius of 10 squared times the 0.1. And just multiplying that out, working that all out, this comes out to be 20 pi. That would be in centimeters cubed. So that's this would be our estimate for the maximum error in the volume calculation. All right, let's take another example. So we want to estimate the amount of metal needed for a square-based box. So I'll draw this kind of square in perspective, where let's see, the base is going to be 10 centimeters by 10 centimeters square, and the height is 15 centimeters. But we have the metal thickness is not the same everywhere. So we want to, when I say amount of metal, I want to know the volume of metal, like how many cubic centimeters of metal is needed approximately, where we have 2 centimeters thick on the sides and 0.2 centimeters, that's 2 millimeters, and 4 millimeters thick on the top and the bottom. Now, the volume of this box is going to be, now I'm going to call this the base, and this B, the base dimension, and this is going to be my H. It's going to be B squared H. That's going to be the formula for the volume of this thing. And I'm going to use differentials for the thicknesses. So dB is going to be this. So dB would be the difference in the base dimensions, which actually you have to be careful because you're going in 0.2 on both dimensions. So it's actually going to be 0.4. dH is going to be 0.4 up top and 0.4 down below. So it's actually all going to be 0.8 altogether. Now the total differential for volume is going to be the derivative of volume with respect to base times dB plus the derivative with respect to height times dH. So this is the derivative with respect to B is going to be 2BH dB. So then the derivative with respect to height is going to be B squared dH. Plugging everything in, we get 2 times the base of 10 times the height of 15 times the 0.4 plus the 10 squared, base squared, times the 0.8. Work this all out and you get 200 cubic centimeters. If you want to know the exact amount of the metal, you can calculate that. If you figure you have a box with the dimensions 10 by 10 by 15, and then you carve out the hollow part in the middle, it's the actual amount would be 10 squared times 15 minus this interior, which, let's see, the base of the emptiness is going to be 9.6 squared times the height of 14.2, and this comes out to be 191.328 cm cubed. This would be our delta V, which is, you can see it's approximated by the differential dv. Okay, as another example then, let's take three positive numbers less than 90. They're going to be rounded to the nearest tenth and then multiplied together. We want to estimate the maximum error in their product. So their product, call it P, is x times y times z, right? And when something is rounded to the nearest tenth, the differential is going to be the difference in the actual value and its rounded value. So the maximum amount that each of them can be rounded would be 0.05, either up or down to the nearest tenth. And that's what we're going to use for dx, dy, and dz. And so we're again going to use a total differential to estimate this. It's going to be the derivative, so px dx plus py dy plus pz dz, right? That's the formula for total differential. And then this is going to be just yz dx plus xz dy plus xy dz. Of course, everything is the same for the dx, dy, dz. And in fact, if you think about this, what's the largest this could possibly be? It's largest when x, y, and z are all equal or close to 90. So we can say x equals y equals z equals 90 for the maximum possible error. And so dp is going to be 90 squared times 0.05 plus 90 squared. So three of these amounts, 3 times 90 squared times 0.05, 1,215. In fact, the largest difference is going to happen when all three of the numbers are 89.95. And so if you think they'd be rounded to 90, 90 times 90 times 90 minus 89.95 cubed. This difference is 1,214.325125, which is pretty darn close to this approximation. All right, well, that does it for tangent planes and linear approximations. And so this is one application of the partial derivative, but the most important one is coming up, and that's the gradient, because that's going to really be useful for a lot of applications. So I'll leave it at that for now with that little teaser in mind, and I'll see you next time. Although I won't see you, but you'll see me next time. See me next time. Okay, bye.